So, okay, the last talk advocated for dynamic pricing, so let me do more of the same. So this is a competition complexity of dynamic pricing, and this is joint work with José Correa, Paul Dütting, and Victor Verdugo. So let me try to introduce and motivate the problem a little bit by a simple example. So our setting is that we want to sell a single item, and the question is just, how should you do it? So let's assume your item is a beautiful painting gifted to you or inherited, perhaps, from some dear relative, but you can't find a spot for it in your house, and now you decide to sell it. And you sell it at a summer yard sale, okay? And let's say things are not going too well at the yard sale, it's a hot summer day, and you don't really have a large number of bidders all gathering around at the same time who wish to participate in your favorite auction, a simple auction of choice. And this leaves you essentially with a second option that might seem a little lazier, but quite natural, and you just slap a price tag on your painting. And well, we want to say that this is not the worst option. I mean, over the course of the afternoon, you might actually get quite a number of bidders who, if they just look at the price tag and the painting, they are essentially participating in your posted price auction mechanism. So you might, in this way, get quite a greater number of bidders, and we want to evaluate how good that can potentially be. So more explicitly, we wish to compare the expected welfare, opt-n, right, of the optimal auction on n bidders who draw IID from some distribution f, with the expected welfare alg-m of the optimal dynamic posted price mechanism on m bidders who draw IID from the same distribution, right? And so dynamic posted price is just a take it or leave it price, and this price may change from one bidder to the next. So we ask explicitly, how big does m at least have to be so that this inequality holds, so that our dynamic posted price mechanism does at least as well as opt-n for all distributions and up to a factor 1 plus epsilon, right? So this kind of comes in two flavors. First, epsilon equals to 0, and we call this the exact competition complexity, and then epsilon greater than 0, and we say this is the approximate version, right? So some related work, one could say that this competition complexity started out with the seminal paper of Bülow and Klemperer in 1996, where they showed that the simple second price auction with one additional bidder gets you at least as much welfare revenue as the optimal auction. Okay? And there has been a string of quite recent work generalizing this result quite directly to the multi-item setting. And so they look at the BCG auction for multiple items and compare it to the optimal one with respect to the number of bidders. Right? And just to say the difference to our paper is that we look at posted price mechanism instead of simple auctions.
And, sorry, your objective is welfare?
Yes, our objective is welfare.
But it doesn't matter, right?
No, so actually our result will hold for both cases, but just for sake of presentation, I'll go for welfare. So our contribution, the first one is perhaps a little bit surprising and negative, actually. So for exact competition complexity, no matter how many additional bidders you recruit to your mechanism, there are some strange distributions for which you will not catch up to the expected welfare of the optimal mechanism. So this is unfortunate, but we have a positive result, more encouraging for approximate competition complexity. And so this one says that if you have at least this number m of bidders that you recruit to your auction, that is greater or equal than 5 epsilon times n, where n is, again, the number of bidders for the optimal auction, then you do get this inequality that we want. So you do have that we get at least as much welfare up to a factor 1 plus epsilon, right? So what is this phi of epsilon? This is this strange integral here, but it's approximately equal to log 1 over epsilon. So it grows very, very slowly in 1 over epsilon. And let me make this slightly more concrete. Right. So on the graph here on the left-hand side, it kind of is good to see what happens when the approximation ratio is already very tight. So if you recruited some number of bidders that got you 99.9% of the optimal welfare, but for some reason you want to do even better than that, right? Then you want to go all the way to 99.99%, then all you have to do is kind of increase your number of bidders from 2.3n to 2.53n, which seems quite reasonable, right? And the graph on the right, what it kind of illustrates is maybe a result that could be overlooked and just from looking at the theorem on the previous slide. And it says that even for the regime where epsilon is actually quite large or the approximation is not so good, our result still holds. And this gives us some interesting corollary, especially if you look at the case of epsilon equals to phi inverse of 1, or in other words, you manage to recruit the exact same number of bidders for your posted price auction as you did for the optimal one. And this kind of recovers the result on IID profits, the tight ratio. That might be familiar to you, and it's equal to 0.745.
I think that was kind of my question, but let me ask it anyway. So basically, if you don't hire anyone, the best thing you can do is the D-Lankier's result or the Correa result,
yes.
And then you will start adding more and more bidders trying
That's
to
right.
identify the approximation ratio you get as a function of the number of bidders.
Right.
Yeah. Cool.
So since we have some time still, let me try to give a brief proof sketch. Right? So our initial question can be rewritten just as an optimization problem, where we wish to minimize this quantity 1 plus epsilon alg m of f, again, minus opt n of f, and over all distributions f. Right? And then just check if this is greater or equal to 0 or not. But right away, we notice that this could be challenging because, I mean, optimizing over the space of all distributions is tricky in general. And moreover, we don't have, in general, a closed form solution for alg m of f. So this also causes a small problem. And let me try to convince you how we, in the end, succeed in dealing with these two problems at the same time. Right? So step one is to partition the space of all distributions by the sequence alg n of f that they generate. Right? So even though we don't have closed form solution for alg n of f, we can show that they satisfy always these three properties for any distribution f. So these three properties are just, these sequences will always be increasing, their difference of consecutive elements will be decreasing, and this ratio of differences will be increasing. Okay? And the converse will also hold. So given any fixed sequence S, okay, modulo some details here, but there will exist some distribution whose sequence alg n will be exactly the sequence S. Okay? And here we get our kind of first convenient property of this particular partition, which is that it has a really simple description, which we'll make use of later on in the proof. Okay? And so step two is that what's remaining is that for a given sequence alg n of f, we wish to identify the worst case distribution G. All right. So what does this mean? It means that if you take the set of all distributions that generate a fixed sequence, right, we want to find among those the distribution that will maximize opt n. All right. And here I made a beautiful drawing for you. So this is just an arbitrary distribution f, right? So the CDF. And at the bottom, I drew its dynamic price sequence, and I called it A. And you can imagine that it goes on past A5, right? And here I give you a candidate G in red that I now try to convince you that it is the maximizing distribution G. So the definition of G is just the average of f on each interval, AI to AI plus 1, right? So in each interval. So we can see immediately that if f is a CDF, then surely G is as well. But we require more of G. In particular, we want that it generates the same sequence. Right? And this is kind of easily seen if you know the second convenient fact in this particular partition, which is that the set of all distributions which will generate the same sequence as as F, so the sequence A, is exactly the family which has integral same as the integrals of F on each interval AI plus 1. Okay? And this is obviously true for the average. So obviously holds for G. And also using this simple description, it's not too hard to show then that finally G is the maximizer of opt n. Right? And now since we have a good understanding of what happens for a fixed sequence, then we can rewrite our problem to this reduced optimization problem. We can now optimize over all sequences instead. But not all sequences, in particular the sequences that satisfy the 3 properties from the beginning, which are now rewritten as constraints just here. And also the objective function now has like simpler form, right? And this is because our distribution G that was maximizing was just this very simple step function. Right? And so we come to one of our main technical theorems, and this just says that, yes, indeed, this reduced optimization problem is equivalent to the original question. Right? So it just says, for any n and m, we have 1 plus epsilon alg m is greater or equal than opt n. For any distribution f, if and only if, the value of the optimization problem is non-negative. And finally, well, we still need to solve this optimization problem, but it is now possible since it looks much more friendly. Right? And we don't get explicit solution right away, but we get instead a recurrence relation. And this turns out to be this decreasing sequence. And the point is to find kind of the index in the sequence where the value of the sequence goes from being positive to less than 0. Okay? And so we analyze the sequence, and we do it by bounding it by a continuous function, and a natural candidate turns out to be an ODE. Right? And this is actually the same ODE as in a recent paper by Correa et al. On posted pricing. But we need to generalize their ideas a little bit to fit our setting. Okay? So essentially, this is all we need for our proofs. And I would like to give some other gaps and additional results. So instead of static pricing, you could also look at, instead of dynamic pricing, you could also look at static pricing, just as in the previous talk. But for us, we get that clearly, since static pricing is, I mean, at most as strong as, or it's weaker than dynamic pricing, we inherit the result of unboundedness for exact computation complexity. Right? This is no surprise. But we also get a lower bound that is strictly worse. So you need at least phi epsilon equals log 1 over epsilon versus log of 1 over epsilon that we had for dynamic pricing. Right? And well, instead of comparing to the optimal auction, you could also compare static pricing to dynamic pricing. And in this case, for the exact version, we get at least n log n, and otherwise it's still open for the approximate version. Right? So very recently, if we come back to static versus the optimal auction, we actually got that this bound of log 1 over epsilon is really the tight one, it's the correct one. And this was a work that was done with additional co-authors, Tomer Ezra and Michal Feldman. Okay. And well, so now we feel that we have understood the single item setting quite well. But so the natural next step would be to go beyond it and some natural feasible multi-item setting. Okay, thanks.
Where does that even come from? So usually those programs are actually like extremely well understood because they're convex and has a nice transformation, which is like.
Yeah, so that's what we use basically, strong convexity at the end of the day. So it's still like infinite dimensional, but we then reduce it. And
yeah, but even in the infinite dimensional case, you often can like talk about the solution.
Yeah.
Okay, but where does that inequality come from? I still don't quite, unfortunately.
So the inequalities, these three, they just come from the properties at the beginning, right? We don't look at all sequences.
Right.
We look only at the sequences that satisfy these three inequalities. And then when we translate it into our reduced optimization problem, that's how the constraints look.
Okay. And this is like just like it was not explained.
Okay. I didn't explain it. It's quite simple, but yeah, I didn't have to.
I guess the question is the ratio between two consecutive deltas should be decreasing in the worst case distribution, and why is that? Because that's where that will go.
That's right. Yeah, but that's a particular like loss complexity constraint, right?
Yes.
Which like gives you a lot of useful properties on the deltas.
Can you explain the relationship between your integral equation for epsilon and like the Helmholtz integral equation that gets the 0.745? So I think you had it on an earlier slide. If you pull it up, yeah. Like I guess if you plug in epsilon equals 0, Yeah. So I mean, this looks a lot like the Helmholtz integral equation, right? So what's the difference? So what's the relationship?
So I think it's basically the same.
Like I think they solved some kind of thing like this to
Yes.
derive the 0.745.
Yeah. So so it is the same, but like I guess just the way we come to it is different. Yeah.
Okay. I guess I have another question. So is it true that if you fix f beforehand instead of letting f change after m and n are decided, is it true if you fix f, when you make m sufficiently larger than n, you can get epsilon equals 0? Like you can
Yes, that's true. So if you do it, if you switch the order, then it's not unbounded anymore. Yeah.
Okay, is there an easy way to see that? Or
is there an easy way to see that? I'm not sure how to explain it in an easy way, but it is.
But it follows from
yeah,
what you're saying.
yeah.
To answer Will's question, so you only look at the epsilon for which m is greater or equal than phi of epsilon times n. So in the Hill and Kerr result, m and n are less m is basically equal to n.
Sorry, I'm saying if you fix f.
Right.
And
So if you fix f first, then definitely this one will change. Yeah.
But two conditions should hold, right? So m should be at least phi of epsilon times n, and then for large n.
So actually, it doesn't. What do you?
Like I'm saying, epsilon is 0, but you get to fix. So basically, I'm saying like you fix the distribution.
Yeah.
And let's say we fix n. So you're like, is it true that for a sufficiently large m, alg is at least oct? And
yes.
Okay, and this follows from your results, but it doesn't like. It's
Well,
not like,
yeah,
okay.
it's not too. It's
Okay.
much easier. Yeah.
Okay.
Two questions. One is on clarification.
Mhm.
Now, you are comparing the optimal dynamic pricing mechanism.
Yes.
Right-hand side is 1. Here it is m.
With the optimal auction, just second price.
But optimal dynamic pricing mechanism, you said that it has no weight.
That's only different.
It has no closed form solution. Yeah.
Maybe it cannot be computed efficiently.
Yes. I mean, it can be computed efficiently by like backward induction.
Yeah, so that leads to my second question. It's like, well, if you consider some simpler dynamic pricing mechanism, maybe you can also consider this.
Yeah, that's true. I guess in some sense, I mean, we're looking at static pricing at the moment. It's very, very simple.